tell us about scattering of gravitational lens fast radio bursts. Let's welcome them.
Thank you. Good morning. So I want to talk about a problem in lensing of FRBs, and specifically I want to address the problem of where are all of the lenses, and this is something Whaley just mentioned in his question. You know, there's sort of this expectation that FRBs are going to be lensed, but we haven't really seen anything to date. And this ordering of the talks today is mildly unfortunate because there are many talks after mine that will be discussing sort of the applications of lensing, but I'm just going to take for granted that it's something that you want to do. You want to see lensed FRBs. And you know, there are many ways that an FRB may be lensed. There's sort of this macro lensing, where you know an FRB is lensed by some foreground galaxy, and you know the optical depth of this is roughly speaking about 1 in 1,000. So roughly 1 in 1,000 FRBs are expected to be gravitationally lensed by these foreground galaxies. You know, there's also micro lensing. If there's some compact object along the line of sight, an FRB may be micro-lensed by that object. The optical depth, of course, depends on how many micro-lenses there are, which is somewhat unknown. You know, for example, you may want to use this to probe how many micro-lenses there are, probing dark matter and such. And so, of course, you know, understanding the systematic effects of, you know, when and why you may miss a lensing event will be very important for using this to constrain dark matter. And then there's also this thing that was just mentioned, where you know it's very likely that for FRBs of some redshift to intersect the circumgalactic medium of intervening galaxies, and there's this idea that that depending on the distribution of the matter in the circumgalactic media, you know, you may get these plasma lenses that actually lens the FRB. You get these sort of dense cloudlets in the CGF that will lens the FRB. And so, you know, there's this question of if there's all of these modes for lensing, why haven't we seen any yet? And of course, the simple answer is that the field is kind of young, so maybe there's no need to sound an alarm necessarily about the fact that we haven't seen any. But maybe it's a little bit curious that there hasn't been any detected lensing event to date. And in particular, there's this effect that has been discussed elsewhere, where you know you have for FRBs, they're not just going to be lensed by some gravitational lens along the line of sight, but there's also going to be scattering that occurs, you know, either with the host galaxy, or you know there may be scattering in the local ISM. So this is, you know, maybe not so much of a problem for, say, in the optical when you're doing these gravitational lensing calculations, because you don't really have to worry about scattering with ionized plasma. But with FRBs, this is very important. And it may have a significant impact on our ability to detect lensing. So this is from a Chime paper where they attempt to look for micro-lensed FRBs and they don't find any. And so they do this calculation where they assume that dark matter makes up, compact dark matter, compact objects make up some fraction of the dark matter, and they do this optical depth calculation. And this left shows the optical depth if there is no additional scattering. But then if you include a scattering screen, depending on the distance, you know, you can get quite a bit of suppression in the optical depth. So you know, this can be quite a significant effect. So I just wanted to talk a little bit about why this is the case. Why does scattering limit your ability to detect gravitational lensing? So you know, here's just a cartoon. You know, you have this, say you have some foreground gravitational lens, and in the absence of scattering, it's going to cause, you know, some multipath propagation. You get these lensed images, and then there might be some scattering screen that is also causing some effect. So you can kind of think of the gravitational lens as being a giant interferometer, right? So here, you know, you can think of it as almost like a double slit. You know, these two gravitationally lensed images are going to basically form an interferometer. And we know from basic undergrad physics that the resolution of a double slit is like the wavelength of the light divided by the distance between the two images. And essentially, the jargon is that when the gravitational lens resolves the scattering stream, then the FRB becomes incoherent. So basically, what this means is that by resolve, I mean, you know, if the interferometer here resolves the scattering stream, then the two images are effectively probing distinct regions of the scattering screen, right? So you can kind of see this on this plot. You know, so this image is being, you know, is probing this sort of region of the scattering screen, which is well separated from this region of the scattering screen. And then you can imagine if you reduce the resolving power of this, these two regions start to overlap, and so they're sort of probing the same region of the scattering screen. So what is the effect of this? Well, the way that you sort of do these searches for lensing is this is what the signal might look like. It's a bit exaggerated, of course, but you say you have some voltage as a function of time, and then this is sort of the initial burst, and then the lensing causes an echo, right? So then you get this sort of echo. And if there's no scattering, if it's just the lens, you expect the echo to have, you know, a phase that's correlated with the initial burst, right? So then you take the autocorrelation function of this voltage, and then, you know, you find that you get these peaks in the autocorrelation function at the time, you know, at this time delay between the images, right? Now, if you have a scattering screen, and if this scattering screen is resolved by the gravitational lens, the effect is that the lensed image, the lensed echo, is now going to have completely uncorrelated phases, right? Because it's probing a completely distinct region of the scattering screen. And now if you do this autocorrelation, that this additional peak disappears, right? So it becomes harder to detect lensed echoes when you have scattering screens, right? Okay, and an alternative way of sort of thinking of phrasing the same thing is, you know, without a lens, without a scattering screen, the FRB is just sort of a point source, and point sources are coherent. But when you have scattering, this point source gets scatter broadened, and there's sort of a limit in which, if the spread is too large, then it becomes effectively incoherent. So that's just another way of making the same argument. So scattering limits our ability to detect lensing, and this is important because, in general, FRBs are scattered by the host environment. We also expect FRBs to scintillate. I mean, we know that some fraction of FRBs scintillate due to scattering in the ISM. The fraction of FRBs that undergo scintillation, you know, depends on who you ask and depends on how they're feeling that day. But the point is that scattering is pretty generic, and so this may have, you know, significant impacts on our ability to actually detect lensing. So maybe that's the end of the presentation, but maybe not. You know, maybe there's some interesting things that we can actually do. Maybe it is not completely hopeless. Okay, so now just to switch gears slightly, we can maybe take lessons from pulsar scintillometry, right? You know, pulsar scintillometry is a slightly older field, so if you want to learn things about the propagation effects of FRBs, maybe it's a good idea to think about how pulsars behave, right? The physics is kind of similar. So this is a famous, to pulsar astronomers, a famous event that was from pulsar 0834, okay, so just as an aside, I will talk about what these secondary spectrum plots are in case you are unfamiliar. But basically the idea is that the observable is the electric field as a function of time and frequency, right? And basically the electric field that you observe is going to be a sum of plane waves, each arriving at the detector with some relative time delay with each other, right? So the voltage you observe is just some plane waves. Okay, now if you take the Fourier transform of these plane waves, you get delta functions, right? So it's actually often convenient to, instead of looking at the observable in this time and frequency domain, to look at it in the Fourier transform space. So basically, if I take a Fourier transform of this plane wave along the frequency axis, then I get a delta function that's localized at the relative time delay between these images. And then if I take the Fourier transform along the time axis, then I get a delta function localized at the relative Doppler shift of these images. So basically, this plot just shows each point here is an image, and that image has some time delay associated with it and some Doppler shift. Okay, thanks. Okay, so I mean the point of this is just that of this event is that this is a similar event in terms of physics as the FRB case, because you have two lensing planes. You have a main scintillation plane and you have an additional lens, right? So it's sort of similar. And if you plug in the geometric values of all of the distances and whatever, you find that actually this is a case where, if using the jargon, the lens resolves the scattering screen. And yet, there's no problem here, right? You might think that in the jargon this causes decoherence, but there's no real issue here. You can find the images, you can detect that there are multiple lenses, you can tell that there is an additional lens. So I just want to bring up two caveats to this sort of simple picture of scattering causing decoherence. One caveat is that when the lenses are one-dimensional and perpendicular to each other, the two lenses actually have completely independent effects of each other and can be completely deconvolved. So there's really no issue there. But perhaps, and that's the case with 0834, the lenses are effectively perpendicular to each other, close to perpendicular anyway. And then the second caveat is that if you have this additional Doppler shift information, well, the lenses in general are going to have create images with different parity, and parity here just means that if the source is moving in some direction, that the image, a positive parity image, moves in the same direction as the source, a negative parity image moves in the opposite direction. So these lensed images are going to have different Doppler shifts relative to these lensed images, and that's what we see. So this is basically, these two islands of power are basically the two lensed images, and they have, you can distinguish them in this Doppler delay plane, right? If you just had time delays, then maybe you couldn't do it. So I guess I should just finish here, but basically this just shows what it would look like if you had a microlensed FRB in this Doppler delay plane. You can see that actually you're able to distinguish between the microlensed images when you have this extra information. But I guess my time is up, so I will just leave the conclusion up here for you to look at.
Questions, Eva-san, please.
Thank you very much. So scintillometry is very interesting, and in order to do that, so I think that there are many FRBs, so dense FRB detections as a function of time to make a Fourier transform. Is it right?
Yeah, that's right. So an additional thing that you need is that you need repeating FRBs, because you need to be able, in order to get this Doppler information, you need to be able to see the scattering as a function of time. So if you just have a one-off, you get the scintillation instantaneously, but that doesn't give you this extra information. So you need repeaters to be able to do this.
Okay, thank you very much for very nice talk. Actually, first part of your talk was really what I wanted to understand. And then I'm sorry, I have a non-scientific question. So you presented the LAM at 2020. So do you have any particular specific contribution to that paper?
Oh no, I wasn't involved in that paper.
Okay, you are introducing the general understanding. Okay, thank you very much. Just for clarification. Thank you very much.
Okay, online question.
Online question from Curtin University.
Yeah, hi Dylan, it's Austin Simons. I'm a big fan of your work. So I wondered you mentioned how basically the angular broadening is kind of a way to think of how the decoherence is presenting. So if the scattering is kind of dominated by screens quite close to the host, kind of within the host galaxy, do you think that's going to have a big effect on lensing in kind of intervening galaxies along the line of sight, or not? So because I guess if the scattering is quite close to the source and the angular broadening is quite limited, then you might still be able to detect these. Is there kind of a sense of scale with these? Do you know what how angularly broadened it would have to be before lensing by kind of like millisecond delays along the line of sight would be effective.
Right, so roughly speaking, so the angular question, I don't have a good answer for that, but roughly speaking, if the time delays associated with the scattering are on the same scale as the time delays associated with the lensing, that's sort of where you get into trouble, right? So you can measure the scattering time scale, you know, and if that is on the order of the lensing time delay that you're trying to measure, that's where you get problems.
Yeah, right. So then in general, if you had some temporal profile that had multiple copies of a burst in it, but the scattering tangles were overlapping, then you wouldn't expect them to be correlated.
Yeah, exactly.
Yeah, okay. Cool, thanks.
Okay, time is up. So thank you, Dina, for the talk.